our previous testing work, when we compare means, whether we're doing z-test or t-test, we were comparing means from two samples. What if I have more? What if I have 3 or 4 groups that I want to look at comparisons behavior here? Well, there's a lot of issues here. I could say, let's say I've got 4 means. In the textbook, page 411, we have 4 different plants that are manufacturing computer chips, and we pull some samples from 10 days production to figure out their defect rates. At the bottom of page 411, I see this. There's an average, there's a confidence interval for each of them, and I want to know, does it matter whether I'm at the Belmont plant or the Cargill plant or the Ardville plant or the Dester plant as to how many defects come out on average? So suppose I've got 4 means, and I want to compare them all. I could do what we did in the past couple of days. I could take any 2 of them, and I could say, what's the comparison between these 2? So if I did that, mean 1 versus mean 2, mean 1 versus mean 3, mean 1 versus mean 4, mean 2 versus mean 3, mean 2 versus mean 4, mean 3 versus mean 4. I would actually have to do 6 different t-tests. And that means I have a higher chance of having an error slip through. Suppose I did a t-test with alpha being 0.05. Well, then the chance that I have a type 1 error is 0.95, right? Okay, back to my probability ideas. If I do 6 different things, chance of making an error is 0.95, and the chance of all of them being right, all of them having no error, would be 0.95. Sorry, 0.05 to the 6th, which is a really small number. I can think of it this way. Probability of any one test having an error is 1 minus the chance of no errors. What's that number? Doesn't help if you can't see it. Yeah.
Would get 0.265.
There's a 26% chance I'm getting it in error. That's a lot bigger than the 0.05 I want, right? This is a problem. If I do individual t-tests, the chance of at least one mistake happening gets bigger and bigger and bigger fast. If I go to 5 means, it becomes 0.4. There's a 40% chance I'll make a mistake. 6 means, it becomes 53%. The more means I want to compare, the worse of an idea it is to do individual t-tests. I would much rather do one massive test and say, can I do all of these at once? And that idea is what the analysis of variance is about. We're going to, oh, wait a minute. You said this number was 0.265? That's too big. The analysis of variance ANOVA, is a comparison of means trying to figure out, is defect rate related to these factors in our production lines. We're going to look at all the possible sources of the variable y. What variation could it have? And we're going to try and see if this is explained by some categorical variable. This is a numerical variable. We're going to call that categorical variable the factor. We can have lots of different factors. We'll look at one factor and then multi-factor later on. Or if that is random random variation, unexplained random error. Sampling variation, right? We had sampling variation when we did multiple samples. So we're going to try and figure out, hey, is the variation that occurs in defect rate due to which plant we are at? But in order to do this, I need to look and see which factors have significant effect on my response variable. Best part. Absolute best part of this whole thing, it uses the F distribution. This is an F test. It's one F test as opposed to 6 or more t-tests. Now, There are lots of other possible ANOVA ideas. How long do you have to stay in a walking boot depends on what type of ankle injury you have. If you look at paint, how thick and gloopy the paint is depends on the temperature. How long does it take to dry? How evenly does it spread? You can look at all these things and say, hey, if the temperature is above 80, between 65 and 80, or between 40 and 65 Fahrenheit, what happens to the paint temperature, what the paint viscosity? But I use ranges so that I can think of it as a categorical variable as opposed to a numerical variable. If I actually want to compare numerical to numerical, I can't do ANOVA, I have to do something else. We'll get there, but not this week. I can test for my factor and say, hey, does this factor have some effect on my response? There are some assumptions I have to make. I have to make sure that my observations are independent of one another. I have to assume or test for the populations being normal. I have to make the assumption that the populations have equal variances. Remember, that changes my degrees of freedom in the t-tests. We'll be able to test to see whether or not we have equal variances. We'll be able to do some observations. But with these three assumptions, I should be able to test for my means directly. I'm going to tell you right now, 100% of the time, this calculation gets done in technologies. I will never, ever do an ANOVA by hand, ever. For me, the most common ANOVA technology is Excel. So I'm going to do every single problem in this entire chapter in Excel. There is a way to do simple ANOVAs on the graphing calculator. There are dozens of other pieces of statistical technology, programming, Jamovi, Python. You can write code for ANOVA in a dozen different languages. It's out there. So I'm not going to bother to do this by hand because the technology makes all of these tedious calculations instantaneous. But really, this example is going to be my driving example. It really works out fairly direct. So in the example I've been talking about, I want to know if defect rate for chips depends on which plant I'm at. So I have a defect rate, that's a numerical value, that's my response variable. I have a numerical response variable, that's my y, and I have a categorical variable, that's my fact. Those, only one thing I want to know that does it depend on. Does it depend on which chip, which plant manufactured the chips. That's why I say one fact. What I'm really doing is making a linear equation problem. I got a lot of observations. I've got all of these different treatments, right? Different plants. Plant 1, plant 2, up to whether I'm doing it in columns or rows, doesn't matter. But I get a bunch of different observations for each one, and then I get a mean for each one. And I get a standard deviation for each one. And now I can say, okay, with all of this information, how can I tell what's effective and what isn't? And what I think of is a linear equation. And I think of the idea of if it doesn't matter, my null hypothesis would tell me that there's no difference between the plants. A null hypothesis, there's no difference. I have 4 averages, right? The average from plant 1, the average from plant 2, the average from plant 3, and the average from plant 4. If I'm right, then that means that the average at plant 1 should be the same as the average at plant 2, should be the same at the average of plant 3, should be the same as the average of plant 4. All the means should really be the same. So what's my alternate hypothesis?
There is a difference in the average defect rate based on plants.
And how would I write that like we wrote our alternate hypothesis for the means test? Hold on. I need to be really specific here about the wording. Yes, there should be a difference. How many?
Maybe just one.
It could be just one. It could be a lot of differences, but there could be at least one. So that means that my alternate hypothesis is there is a difference. At least one of the means is different. And I don't know which one. It might be that only one of them is different. It might be 2 of them is different. It might be they're all different. It just means at least one of them is different. Okay. By our assumption, I want to think of this as a line. I could say, all right, the Y value, chip defect rate, should have some global mean. And then maybe there's some effect due to this treatment T a treatment is a combination of factors. In this case, we only have one factor, so there would be T1, T2, T3, T4. And then there's some random error. Now you'll notice I put some subscripts here. The hell are these subscripts about? Well, really, I should go back over here and put the I and the J as subscripts over here. These subscripts represent the different observations I did, that's I, at each treatment, each plant, J. So J is the number of factors. I is the number of data gathered per factor. If we go back to the top of page 414, where I pointed out all that data we got in columns and rows, all that data we got in columns and rows, you'll notice, I'm going to put this over the text here, has two subscripts on it. At plant 1, we had a bunch of observations. We had Y11, Y21, Y31, Y41. Those were at plant 1. And at plant 2, we have Y12, Y22, Y32. So Yij is the ith observation at location factor J. If my null hypothesis is correct, then these are all 0. Because that's what it means for the factor to not matter. That the effects are all due to random error as opposed to something related to which factory I'm working on. Please understand that this then requires me to do an absolute crap ton of calculation. For each of the observations, I figure out the average in each group. I then split up and take the overall average. I then think of the error between each observation and that overall average as the part that's related to the little factor and the part that's just random error. And then I got to do, I mean, literally a whole bunch of summation and degrees of freedom, and I end up with an F value. I am never, ever going to do this by hand. If the individual means are not all that big, then I'm going to get an F value and a corresponding P value for that, right? I'll have an F left and an F right, and I have degrees of freedom for both of those things. Okay. I have an example. Boom. I have 4 workstations responsible for packing shipments. And here's how many cartons they pack on average over the course of a couple numbers of days. If the same people work the same station every time, is there a difference in how well they pack based on which station they're at? I got a sum, I got an average, I got a standard deviation. for 5 different days. I looked at every day this week. I've got the average for all 5 days. Let's figure out how they did. Before I do any actual analysis, it might be to my benefit to take these 5 sets of data and plot them. Day 1, day 2, day 3, day 4, day 5. How many boxes did you plot? Did you pack? Here. Station 1, 2, 3, and 4. There are the packing values for each of these stations. And I say to myself, over time, can you tell just looking at this whether or not one station is consistently better or worse than another? What do you think? Kind of hard to tell from that, isn't it? Whatever was going on at station 4 had something bad happen in the middle of the week, but they started out better than station 2, and station 2 had a great middle of the week. I don't know. So maybe there's something going on here, maybe there isn't. If we see clear distinctions between, hey, this curve is always on top, this curve is always on bottom, but these are crossing each other in a bunch of places, I'm not sure that this helps me very much. I want to run a test. I want to know if the average packing rate is different based on station. So I'm going to go into Excel. Here's my data. Let's make it so you can actually read some of this crap. There are my numbers. What I don't have here that I did have in the book is I don't have the averages. I don't have the standard deviations. I don't have the counts, but I can work this out. Before I go on any further, I need 3 things. I need a null hypothesis. If I'm doing an ANOVA, what is my null hypothesis going to be? Same every time.
There's no difference.
There's no difference. And my alternate hypothesis, therefore, is at least one is different. Doesn't tell me which one, but at least one is different. I need an alpha. I need to know how sensitive this test is. How significant is significant enough? How big a difference is big enough? We can use any alpha we've used before. We have an F table for all sorts of alphas, right? 0.1, 0.05, 0.025, 0.01. Let's use 0.05. It's the default setting most of the time. So I now know what I am testing, my hypothesis. I know when I'm going to decide. I'm going to decide to keep my null hypothesis or reject it based on what? This is an F test, just like we did on Wednesday. When I do an F test, I either need the F critical values, F left and F right, or I need a p-value. When do I reject my null hypothesis? There should be a picture in your head. A shaded curve. When do I reject? I either reject if I'm outside the shaded area, or if I have a p-value. What do I need to know about the p-value?
Bigger or more than
One of those will be reject, one of those will be keep. Which one's reject?
if it's inside the shade, we can reject.
Right, but now I'm thinking about p and alpha. It's either bigger than alpha or smaller than alpha. One of those is reject, one of those is keep.
Bigger.
Is if it's bigger, it's
Keep.
keep. If it's smaller, it's reject. So I'm going to do an ANOVA on that data that's shaded in there at the top. I'm not going to do this by hand. I'm going to go to the data tag. And I'm going to go, okay, data, under data analysis, go up to the top. Right at the top there is an ANOVA single factor. The only factor that matters here is which plant I'm at. I'm going to click on that. And now I'm going to say, where is the data? The data is here. It is in columns, not rows. The labels are the first rows. And then I put my alpha in. Right now my alpha says 0.05. If we want to change that, we can. I need pretty good reason to step away from alpha being 0.05. Almost all of the statistical analyses done in this country are done with alpha being 0.05. Whether they're ANOVAs or means tests or any other tests, almost all of them are done at 0.05. Now I'm going to have all of the output stuck on a new worksheet, but you could put it somewhere right in the middle of this page if you wanted. Just don't overlap the data if you choose to. New worksheet apply, go. So it's done the ANOVA. And notice what it tells me. It tells me at the top here, the average, the variance for each of the stations. That's just a summary of the data that was actually in the textbook on page 417, where we had the data given to us. But now at the bottom, this is where the ANOVA test itself is done. Because that's the discussion. Is there more variation between the groups or within the group? Because variation within the group should be the random error part. Variation between the group, that's where the treatment matters. So what we're weighing is the difference between the error generated between the groups and the error generated within the group. And when there's more error between the groups, based on degrees of freedom, than there is within the group. And that's where the degrees of freedom matter here. There are fewer groups, there's a lot more numbers altogether. That's why the degrees of freedom is so much bigger within the groups. And I go over here to the right. And there are 3 numbers that will tell me everything I need to know. Right here. What Excel has done is a right tail folded f-test. Because I want to do a 2-tail test, and a 2-tail test would test out, is one of them different low or is one of them different high? But rather than automatically do a 2-tail, it folds it every time and just does a right tail test. And that's why there's one critical value. That's an FR. That means I need to be bigger to be in the rejection region, Leo. I need to be up above in that shaded region. But my p-value needs to be small for me to reject. Based on those 3 numbers, what should I do in this case? Keep my null hypothesis or reject it?
How much was alpha?
0.05.
Who rejected?
Because my p-value up there is 0.025. Or my critical value is 3.238. And my actual calculated value is 4.12. So I'm in the shaded region. I'm above my critical cutoff. I should reject. What does that mean? That I rejected my null hypothesis.
There is a difference.
There is a difference by location. One or more of these stations does generate a different number of boxes packed than the others. And you can actually go up there and look now in the summary, based on the summary data. Look at the averages in the different stations. In station 1, my average is 242. In station 2, my average is 246. Stations 3 and 4, my average is in the 220. I've got 2 in the 240s, 2 in the 220. Looking at the curves, I couldn't see that. But there is clearly a difference here. 1 and 2 are much higher than 3 and 4. The fact that it was 2 and 2, I would never have guessed. And if I'd done individual t-tests, 1 versus 2 would have said no difference. 3 versus 4 would have said no difference. But 1 versus 3 or 1 versus 4 or 2 versus 3 or 2 versus... So I would have had to pick just the right t-tests. No, there is a difference. That's a pain in the neck. Whereas doing one test and then after that, analyzing what happened as a result, that's useful. Now, in the textbook, it literally takes 2 pages to walk through the calculations that we did in 3 clicks. People, I have never in my entire life done an ANOVA calculation by hand. Even when I've done them for things I thought was going to be important and would take a long, no, I shoved it into a computer and gave it to me. We had a very large class at the University of Pittsburgh. When I taught back in 2000, 2001, I was working for the professor who taught the business calculus class. The business calculus class was 640 students. There were 4 different lecturing instructors. There was a morning class, a mid-morning class, a late afternoon class, and a night class. And we wanted to know if your score on the final exam, because we gave one final exam to all 600 students, depended on which teacher you had. It turned out that it actually mattered more what time your class was, because one of those teachers taught 2 of those courses, the late afternoon and the mid-morning. So there was actually a different factor. But we did this sort of factor analysis on 640 records. I didn't do this by hand. Boop. Does final exam depend on who your lecturer was? Here are 4 different majors in the School of Business. Does GPA depend on major? Now, I don't know if you give a flying a rolling donut about your GPA. You get a degree, you get to get out of here, you're graduated, right? There are a lot of people who say, I got out, I'm done. Good. There are some people like, I got out with a 4.0, I'm going to keep that at the top of my resume for the rest of my life. Does your choice of major affect your GPA? Now, this happens to be just for a single semester, as opposed to across the entire time. But I could ask that same question. Do you believe accounting majors or finance majors or HR majors or marketing majors have significantly different GPAs from each other? Let's find out. And get rid of this one. Get rid of the blank. I don't even know why I had it up. Here's our data file. It is in our canvas page under class examples. Let's see what happens. Before I go anywhere any further, it actually asks me to compare these. It doesn't give me an alpha. What's my default alpha?
5%.
5%. 0.05. So I would like you, if you've got your computer open with you, to run this ANOVA. If you don't have it with you, you should make sure that you make down question 7, GPA, and do this one later so you know that I'm not pulling something fast on you here. I go to the data tag, data analysis, ANOVA, single factor, because the only thing I'm checking on is choice of major. I've got my data in columns here. And I highlighted the top row, so I'm going to make sure I click the thing that says labels, so it knows that the labels are in the first row. My alpha is still 5%, 0.05. I'm going to put all the information in a new worksheet. New work page. Since these numbers are a lot smaller than the numbers we were looking at before, I didn't think it was useful to graph the line graphs of each one, but we can do that as well. But there isn't really an order to this data like there was in the observations of the boxes and the stations, because that was chronological, day 1, day 2, day 3, day 4, day 5. This really doesn't have a chronological across. My null hypothesis is there is no difference. No, there's none of a difference. Your choice of major does not affect your GPA within these 4 in the School of Business. My alternate hypothesis, at least one is different. So we ran the numbers. In the bottom section, that's the ANOVA analysis of variance. That's where my answer is. What's that set of information tell me?
And we should reject the output
Because
because the p-value is less than 5%.
p-values are smaller than 0.05. I reject. And that means
There is a difference.
at least one of the averages is significantly different than the others. And then I can go back and I can look at the top and I can say, oh, well, accounting's a 2.8, marketing's a 3.3. Yeah, it seems like it goes up by like 0.2-ish no matter when you change majors, right? So one of these majors is clearly harder than the other three. Well, maybe it's like they're all different enough that there isn't a gross grand mean. And that was what our linear model idea was saying. There should be a grand mean. And if it's affected by the different things, that'll change it away from being a uniform mean across the whole setup. Yes, my critical value is 3.008. My calculated value is 3.517. I'm in that rejection zone. My p-value is really small. Out we go. Now, this could be taken as a criticism of the accounting faculty at this institution, Oxnard University. Right? This is Oxnard again? Yes, Oxnard University. The accounting people are just too damn hard if everybody's getting a 2.8. You know, that's a C plus average. That's not great. B minus average. Or it could be taken as criticism of the marketing department. Everybody's earning an A minus average there. You people are too easy. We have to figure out which way this is going to go. But I now have the ability to say, I ran the test. This is what it tells me. There are a couple of specific additional tests we can do that will allow us to figure out where the differences are more precisely. The statistical software in Excel doesn't do these easily. A gentleman by the name of Tukey, whose first name I forgot, and a gentleman by the name of Levine, gentleman by the name of Hartley, all came up with additional ways to dig deeper and figure out exactly where the differences in means are significant and where they aren't. It's almost like just doing all the paired t-tests. But there's a little bit less work to do because you've already done an ANOVA. That's easier to do in things like Jamovi or forgot the name of the other, Jana. It's another Jamovi related idea. Or to code in Python. It's not really what I want to cover. On the other hand, having two different things that might affect it. What if I'm thinking about those chip manufacturers again, right? What if instead of just having 4 locations, I also had 3 8-hour shifts? There's a group that works mornings, there's a group that works evenings, and a group that works overnights. That way the production stays on 24 hours a day, right? I want to keep making chips. So now I have 2 things that matter. Which plant are we at, and which shift are we on? I'm going to go downtown. I get in call an Uber, and I say, take me downtown. I get a bunch of different drivers, right? And they could choose a bunch of different routes to go. If I am always going to the same place, does the choice of driver matter? Does the choice of route matter? Does those 2 together matter? That's what I want to look at starting on Monday. I will see you all then. Have a wonderful rest of your day and enjoy your weekend.